Alright, Assalamualaikum warahmatullahi wabarakatuh, and a very good morning to everyone. So how is everyone doing?
I'm doing okay.
Okay, so alright, just want to make sure that everyone receives the audio and video from me, especially the screen share. Alright, good to hear from you guys also. Good morning, Witness. Morning, Lee. Morning. So we are still in our current chapter, which is the orbital perturbation, and what we have done so far is, I would say what you have done so far is you have thoroughly learned about two things: Julian dates, and also so one is, I think you learned Julian date, and the other one is one and two. So sidereal time. Okay, so it's denoted by a funny theta right there. So Julian date, you have done you know how to calculate that. You even have made your own program to calculate Julian date. The same thing for local sidereal time also. Okay, so right now those two are just the basics, yeah. Pretty much the basics of finding time in Julian date, and also finding the local sidereal time. Okay, pretty much your position also. So next one, what we are going to do is this. So let me tell you the problem first. Okay, so let's say, for example, if you look at this picture right here, let's say you see something in the sky. So in this example, it's the sun, but it could be anything. It could be a satellite, for example. Yeah. If you see this and then you know some related properties of this, well, celestial object, you know its position in the sky, okay, and also you know its the rate of how fast it's going, for example. Yeah, so let me see. Okay, so we are going to use for position, for example. Oops. So for position, we are going to use two angles. One is called azimuth angle, denoted by the letter A, azimuth angle, and the other one is denoted by small a, not to be confused with semi-major axis, but let's look at that one. So A is what we call the elevation angle. Okay, so elevation angle. Okay, so as you know, that you need probably a degree or radian, it's up to you. Okay, so how do you cut, for example, if you see a celestial object like this one here, okay, how do you explain their position? Two angles, azimuth angles and elevation angle. How do you calculate azimuth? It's the angular distance from north to that position. So for example, let's say you are standing on the ground here. Okay, you know this is the direction of north, this is south, this is east and west. Let's say you see something in the sky. See, this is looking from top to bottom. Yeah, you are here, so this is your head here. So let's say the position, you saw something in the sky here. So azimuth angle would be the angle from north to the position of that celestial object. It has to be in clockwise direction. Okay, so this angle right here, this one is, sorry, this one, this is the azimuth angle. Okay, now this is the angular distance on the ground. Now let's say this is the horizon. Okay, this is horizon, and then you see something that is up in the sky like that. Okay, so here, this is such a ugly shape. So let's say this one here. Okay, so this here, you might say this is the altitude, but it's more it makes more sense if you denote that as an angle. So angle from the horizon to the thing that you're seeing. So this angle here is called the elevation angle. So if you see something in the sky, for example, you need to tell me two things. One is the azimuth angle, the angular distance. You know where the north is, and then you calculate the distance, angular distance, that's at the azimuth angle. And then from the ground up, okay, from the ground up, that is the elevation angle. Let me see if I can find another picture just to show you here. Let me see. Okay, azimuth elevation. Okay, I think this is more like it. Okay, so let's say you're standing in the middle right here. You know where north is, and then you see something in the sky here. So the angular distance from north to the object on the ground. Okay, so you project a line here, that is the azimuth angle, and then from the ground up, that's elevation angle. So in this diagram, it's shown as alpha and E, but we are using big A and small a. Okay, so let me see if I can find any other pictures just to maybe give you a bit more. Yeah, this is the picture where I got it from. Yeah, I think this one makes okay, but it's kind of weird because it's not following any north or south. Okay, you can think of it this way also, same thing, but right now it's here, it's using altitude instead of elevation, but it's the same thing. Okay, so you see something in the sky, you are here in the middle, observer, whatever you see in the star. Okay, you can explain the position, you can describe the position using these two angles. So that is on azimuth and elevation. Now our problem here is this. Let's say you are sitting in for example, this is your observation site. Okay, observation site. Let's say you observe something from our space lab. Okay, so you observe something from UPM Serdang. Okay, it's observation site, and then you see some object in the sky. So you know the azimuth angle A is some value, okay, a degree, okay, and then you know the elevation of that object in the sky, denoted by a degree. And then you know also that that object in the sky is moving with a rate a dot degree per second, okay. And a dot degree per second. Now let me draw you here, and then you watch something in the sky, okay. And this object has its a, its small a dot, the rate, and a small a dot. So you observe something in the sky, and you know its azimuth angle, elevation angle, the rate of change of azimuth angle, and the rate of change of elevation angle, okay. So the question is now, can you determine its orbit, which means can you determine the semi-major axis, E, I, small omega, big omega, and theta, okay. Be careful, there's a difference between this A and that A. It's gonna be confusing if you use, we ran out of letters anyway. Oh, by the way, this is different, okay. So the question is this: you are standing here in UPM Suriname, for example, you see an object in the sky, you know its azimuth angle, elevation angle, the rate of change of azimuth, the rate of change of elevation. Can you determine its orbital elements, AEI, small omega, big omega, theta? So this is the core of what we are doing here in this chapter. So this is what we call preliminary orbit determination. We want to determine the orbit of an object in the sky based on what we see from where we are, okay. Before, what we have done is you are given the vector r and the vector v, the state vectors, okay. You're given position vectors and also the velocity vectors, and you know these two vectors are based on the geocentric coordinate frame, which means you're standing here in the middle here, and then you know your r whatever, okay. So that is, well, that is very ideal, because you perhaps by using some kind of observation, you can figure out the radius in the in the geocentric coordinate system and the velocity in the geocentric coordinate system, but that's usually not always the case. So usually what you do is you sitting here, okay, on the surface of the earth, and then you see something in the sky. So usually that's what happened. You don't sit in the middle of the earth and then you calculate the r like that. Usually what you do is, well, you sit somewhere on the surface of the earth and then you observe something, and then what you got here usually is just this one. You only have probably these 4 numbers only, okay. So it's different from getting this. So this we don't know, okay. So the question still remains, if you got these 4 numbers here and you know where you're standing, okay, can you determine its orbit? So this is the task that I need you to actually again come up with the algorithm. Well, not really come up with the algorithm, but I've already written the step-by-step I would say the the code. Okay, let's see. Where is it? Here. So this is our next task here. So orbit determination. Okay, I introduced to you two new coordinate systems where the origin is not at the center, okay, but your origin is here on the surface of the Earth. Okay, it's really more realistic for you as well. So what we are going to imagine here right now is this here. As you can see here, you can see that's the azimuth angle, and then that's how you imagine the elevation angle. Okay, and then you see an object B in the sky. Okay, and then that's your two angles. Okay, now so the problem, let me formalize the problem that I've told you just now. So informally, I would say you see an object in the sky, you know its azimuth and elevation angle, you know their rates, you need to find the orbit elements. But let's formalize that. So let h, altitude, latitude, remember your latitude is different from longitude, and the local sidereal time. You're really familiar with this now by now. Okay, respectively of a ground station. So for example, if you are in UPM, you need to know what's our altitude, how high are we from the sea level, okay, and what's our latitude, and what's our local sidereal time. Okay, these two numbers, you can find it, probably you can Google these two numbers. Okay, what's our altitude currently? I think our UPM Serdang is probably almost sea level. So if it's sea level, then h is 0. If you're on top of Mount Everest, for example, altitude would be 8 kilometer, 8 something. If you're on top of Mount Kinabalu, 5 something kilometer. Okay, latitude you can still find it on Google, but this one you have to use your calculator. All right, so let's say these three, you can find these three. Let's say you observe an object at 2 p.m. on last Tuesday, for example. You can find the local sidereal time. Now given the range here is this here, range here is the distance between you, yourself. Let me delete everything here. So range is, because you can see there, the distance between you and the object, that is distance. Okay, so rho. So let's say you're given that rho, range, azimuth angle A, elevation angle A of a body B. Okay, given also at their rates with respect to time, so you know the distance rate, you know the rate of azimuth angle, how fast it's moving, and how fast the elevation angle is moving. Write a program to calculate the state vectors R and V of the celestial body from the given information. So you get 6 information, you can get another 6 information. Why I say 6? Because you remember R is a vector, yeah? Rx, Ry, Rz. Okay, and V is also. Oh my god, my handwriting on this one is so terrible. This is so terrible. This is really terrible. Anyway, 6 elements from 6 numbers. And use the program from your previous assignment to calculate the orbital elements. Okay, so basically your job is to do this. So it's a big project here. So your job is, you get these 3 numbers. You got not that one. You got rho a and small a elevation, their rates of change. Okay, and then from here you need to find the state vectors in global coordinate frame. Okay, and then finally you need to find all the orbital elements. So 3 steps. Okay, so you need to find a program. This is the input, so I would say this is the input, and then your output will be this one here, final output, but you have to go through the process number 2. Okay, so this is your task for this one. Don't worry, I have already listed the step-by-step procedure. Okay, but I wrote it in terms of formula like this. So let's see how many things we're doing. Is there a question? I hear some noise. Okay, so let's see how many. Hello. Okay, let's see how many equations that we need to deal with. How many steps? 1, 2, 3, 4, 11. Okay, but that's 11 steps to R and V. 11 steps from here to here is 11 steps. Okay, let me see. So from here to here, there's 11 steps. Do you still remember how many steps from here to here? I think there's about 13 if I'm not mistaken. Okay, so I think let's do this first from 1 to 2. So what's presented here, steps 1 to 11. These are, the point is to given this here, you need to calculate these two. Okay, so you can see that it involves a lot of sine angle and everything. So now if you want to, again, I got an example here. If you want to check your code, let's say you put all these numbers here, and then your answer will be these two. Okay, let me tell you that this same exact example, you can find it in the Curtis textbook. Okay, it's just so if you want to check whether your calculation is correct like last time, you can check this example right here. All right, so let me stop right here and ask you if do you have any question on this next task. Nope. All right, cool. So 24, yeah. Here's the thing, Lee. Let's try doing the first algorithm. I mean, from the given row, big A, small a, row dot, big A dot, small a dot, and find the state vectors first. So let's start with the first 11 steps. First 11. Okay, and I want you to do this in the same spreadsheet that you were using, that you used for the local sidereal time Julian date calculation. Same thing, just add the sheets. Okay, so for example, if you have so for example, if you have your calculator last time, yeah, this one here. Why do I have this in my, anyway, oh, probably you shared it with me. Okay, let's look at this part here. Okay, just add a new sheets here. Okay, so just leave these two, or however many you have it in your previous project. Let's add another one here. Okay, let's add another one here. because you're gonna use this one as well, because you need to know your city here, for example. Okay, all right, maybe you need to choose. Oh man, this is not in alphabetical order. No, how do I find things? Anyway, let's say your site is in Nairobi. Okay, so you're gonna have the local sidereal time here, so you're probably gonna have to use this. Okay, so relate that to your calculator here, and then do the first 11 step first. So do not go into the next 13 steps yet. Go for the second algorithm first. Okay, the one that I've given you. So the algorithm, I've given it in I think to do. What was it, to do? Yeah. So everything is in here. Okay. This file right here, okay, is in here. Part Dukes. Okay, you're gonna have to tell me how to pronounce this. So this is it. This is the file. Again, let's try and do this the same way we've done the previous one. Let's do it together. Okay, and then use the same group, use the same file spreadsheet, so that you don't have to create too many. Okay, so if I want to see it, so I'll just probably just click on your links here. Okay, so that is for the next task that I told you about. So let me just again stop here, and then to ask if you have any question to ask. So far so good, yeah.
Yes.
Okay, thank you. Thank you, that someone, because sometimes I need vocal feedback. Doctor, once we find the RNA vector, can we use it? Oh yes. That is actually the reason why I want you to do this. So I answered that with a big yes. A big yes. If you have done something from I think before, I think some of you have also written this program on a spreadsheet. I think some of you have written this in Python, I think. So so you already have that from RV to orbital elements. So you can use that straight away. So for Cleanest, I think your group one part is already done. You already have your orbital elements calculator. Right now what you need to do is have an algorithm to calculate from the observation into state vectors. That's it. Okay. I need to tell you about one thing. When you're dealing with the sine function or and/or the cosine function in Excel or spreadsheet, sorry, we don't call it spreadsheet, in sheets or Excel. Okay, the units, the default units is in radian, yeah. Okay, so be careful. You need to actually, if you got something in degrees, you need to well, any calculation on using the function, sine function and cosine function in Excel and sheets is in radian. So whenever you get something in degree, you need to change it to radian and feed it through the function. And then whatever the answer, for example, if you're using cosine or arc sine, you need to convert the answer back in degree. So be careful about that. Okay, it won't, the default unit is in radian. So, well, you know how the deal is. You can always convert degree to radian. You know what to do. Okay, thanks Mike Hawk, brother of Tony Hawk, for pinning the message. Okay, this is important. Not only sine and cosine, but all trigonometric functions, they are all in radians. Yeah. Okay, except for the one before that we have done. That one is in degree. Yes. The previous assignment that we did, that one is okay. In the future, because here you see you'll have a lot of degrees here. Yeah, weird. Oh man. Okay, so you need to be careful with that one. Okay. All right, so I will just probably stay another 2 minutes if you have any questions. If not, you can always go ahead and plan with your group mates on how to proceed with this lah. So I would like to mention again, this is an online collaboration. One of the learning outcomes that you need you'll get from this is how to work in a team in an online environment where you don't see each other very much. Okay, so this is the new norm. Perhaps in your working environment later on you'll be doing a lot of this, so why not just you know, train to do something like this. Okay.